What if I told you that you're currently falling through space at over 2 million kilometers per hour, trapped inside a cosmic whirlpool that's simultaneously eating itself alive and preparing to collide with another galaxy at that exact moment? And here's the truly mind-bending part. This catastrophic collision has already begun. And here's the truly mind-bending part. And you won't live long enough to see it end. Welcome to the secret life of galaxies, where everything you thought you knew about these beautiful spiral structures is about to be completely shattered. Look up at the night sky. Those peaceful, static pinpoints of light, they're lying to you. What you're actually seeing is a cosmic battlefield where galaxies are born in violent explosions, cannibalize their neighbors, and transform themselves through processes so slow that entire civilizations rise and fall in what amounts to a single frame of their story. In the next 3.5 hours, I'm going to reveal how the very structure you call home, the Milky Way galaxy, is a living, breathing entity that's currently in the middle of consuming at least 5 smaller galaxies. And we're all riding along one of its spiral arms like passengers on a cosmic roller coaster we never bought tickets for. Here's what will blow your mind. Galaxies don't just exist. They evolve. They're born, they grow, they interact, they merge, they die. And the process is so incredibly complex that scientists are only now beginning to understand that everything we thought we knew about galaxy formation for the past 50 years might be fundamentally wrong. In 2022, the James Webb Space Telescope sent back images that showed fully formed galaxies existing just 300 million years after the Big Bang. These galaxies were supposed to be impossible. They were too big, too organized, too mature. It's like finding a fully grown oak tree in a forest that was planted yesterday. But before I reveal how this discovery is forcing us to rewrite the entire timeline of cosmic evolution, let me ask you something. If you could watch a time-lapse of our galaxy from its birth 13 billion years ago until today, compressed into just 1 minute, what do you think you'd see? Hold that thought, because the answer is far stranger than you can imagine. If you're already feeling that tingle of cosmic vertigo, hit that like button right now, because we're about to go much, much deeper. Subscribe and turn on notifications, because this journey through galactic evolution is going to challenge everything you think you know about the universe. And I want to know, where in the world are you watching this from, and what time is it there? Drop your country and your local time in the comments. I love seeing how this content reaches people across the globe. From Tokyo at midnight to London at breakfast time, all of us contemplating the same cosmic mysteries. Now, let's begin at the very beginning, but not where you think. To understand how galaxies are born, we need to travel back to a time when galaxies didn't exist at all. I'm talking about the period roughly 13.8 billion years ago, just after the Big Bang. But here's the twist that most people miss. The universe immediately after the Big Bang wasn't ready to make galaxies. It was too hot, too dense, too chaotic. It was like trying to build a sandcastle in boiling water. For the first 380,000 years after the Big Bang, the universe was opaque. Photons, the particles of light, couldn't travel freely because they kept colliding with electrons in the hot plasma that filled all of space. This period, called the photonic epoch, was essentially the universe's infancy, a time when nothing could form, nothing could be seen, and nothing remotely resembling a galaxy could exist. Then something remarkable happened. The universe expanded and cooled enough for electrons to combine with protons and form the first hydrogen atoms. This event, called recombination, suddenly made the universe transparent. Light could finally travel freely. This is the light we now detect as the cosmic microwave background radiation, that faint glow coming from every direction in space, the afterglow of the Big Bang itself. But here's what will blow your mind. Even at this point, the universe was almost perfectly uniform. Almost. If you could have looked around during this time, you would have seen hydrogen gas everywhere, all at the same temperature, all at the same density. Except for tiny fluctuations, tiny quantum ripples from the earliest moments of the Big Bang, variations in density of just 1 part in 100,000. These microscopic imperfections were the seeds of everything. Every galaxy, every star, every planet, every person traces their existence back to these quantum fluctuations that occurred in the first fraction of a second after the Big Bang. Think of it like this. Imagine a perfectly still pond. Now drop a handful of sand into different spots. The sand particles will start to attract more particles, creating small mounds on the pond floor. Those tiny quantum fluctuations work the same way, except instead of sand, we're talking about dark matter and hydrogen gas. And instead of a pond, we're talking about the entire universe. Here's where it gets interesting. The denser regions had slightly more gravitational pull. This meant they attracted more matter. As more matter collected, the gravitational pull increased further, attracting even more matter. This process, called gravitational collapse, was slow at first, but it was inevitable and unstoppable. The rich got richer. Dense regions got denser. Now, I need to introduce you to Vera Rubin, an astronomer who in the 1970s made a discovery that would fundamentally change our understanding of galaxy formation. Rubin was studying the rotation curves of galaxies, measuring how fast stars orbit around galactic centers at different distances. According to Newton's laws of gravity, stars farther from the center should orbit more slowly, just like planets farther from the sun orbit more slowly. But that's not what Rubin found. She discovered that stars at the edges of galaxies were moving just as fast as stars near the center. This should have been impossible unless there was far more mass in these galaxies than we could see. The visible matter, the stars and gas, simply didn't have enough gravitational pull to keep these fast-moving outer stars from flying off into space. Rubin's work provided some of the strongest evidence for dark matter, an invisible substance that doesn't emit, absorb, or reflect light, but has mass and therefore gravity. Here's the mind-bending revelation. Dark matter makes up about 85% of all matter in the universe. Everything you can see, everything made of atoms, every star, planet, and person, is just the 15% minority. Galaxies aren't primarily made of what we think of as normal matter. They're mostly made of something we can't see, can't touch, and still don't fully understand. This changes everything about galaxy formation. When those first quantum fluctuations began to collapse under gravity, it wasn't just hydrogen gas falling together. It was primarily dark matter collapsing first, creating gravitational wells, like cosmic sinkholes, into which normal matter would later fall. The dark matter formed the scaffolding, the invisible architecture, upon which galaxies would be built. By roughly 100 million years after the Big Bang, the first dark matter halos had formed. These were enormous clumps of dark matter, typically containing the mass of about 1 million suns. Within these halos, hydrogen gas began to collect. As the gas fell into the gravitational wells, it gained energy and heated up. But it also started to radiate that energy away, cooling and condensing into denser clouds. This is a crucial point that many people miss. For galaxies to form, gas needs to cool down. Hot gas has too much internal pressure and resists collapsing further. But as hydrogen atoms collide with each other, they emit radiation and lose energy. The gas cools, pressure drops, and gravity can pull it together more tightly. It's like the universe had to wait for things to cool down before it could start building anything substantial. Around 200 million years after the Big Bang, in the densest, coolest regions of these dark matter halos, something incredible happened. The first stars ignited. These weren't stars like our sun. These were monsters. Population 3 stars, as astronomers call them, some containing hundreds of times the mass of our sun. They were made of pure hydrogen and helium, because heavier elements didn't exist yet. They burned incredibly hot, incredibly bright, and incredibly brief. The largest ones lived for only a few million years before exploding as supernova. But here's the critical part. Those explosions created and scattered the first heavy elements into space. Carbon, oxygen, Iron, silicon, all the elements that would later become planets and people, were forged in the nuclear furnaces of these first massive stars and distributed by their deaths. These explosions also sent shockwaves through the surrounding gas, triggering new waves of star formation. This is how the first protogalaxies formed, not as grand spiral structures, but as small, chaotic collections of the first stars, embedded in dark matter halos, surrounded by clouds of gas, now enriched with heavy elements. These protogalaxies were tiny by modern standards, containing perhaps a few 100 million stars, compared to the hundreds of billions in galaxies like the Milky Way today. And here's what nobody expected. These protogalaxies were violent, turbulent places. The massive stars exploded frequently, generating powerful winds that could blow gas out of the protogalaxy entirely. Star formation was erratic and inefficient. Many of these early structures probably failed to become galaxies at all, their gas stripped away by the energetic feedback from their own stars. What I'm about to tell you next explains why those James Webb images were so shocking, and it's going to change how you think about cosmic evolution forever. Remember those impossible galaxies Webb discovered, the ones that were too mature, too soon? To understand why they broke our models, we need to talk about what astronomers call hierarchical structure formation, the theory that dominated our understanding of galaxy evolution for decades. And I'm going to show you why that theory is now in crisis. The hierarchical model seemed elegant and logical. It said that small structures form first, then gradually merge to form larger structures. Protogalaxies merge to form dwarf galaxies. Dwarf galaxies merge to form galaxies. Galaxies merge to form galaxy clusters. It's bottom-up construction, like building a house by first making bricks, then walls, then rooms, then the complete structure. This made perfect sense and was supported by our understanding of how gravity works and how dark matter clumps together. Computer simulations based on this model could reproduce the large-scale structure of the universe remarkably well. They predicted a cosmic web of dark matter filaments connecting nodes where galaxy clusters form. And when astronomers mapped the actual distribution of galaxies in the universe, it matched these simulations beautifully. The model seemed to work. But there was a problem hiding in plain sight, and it took the unprecedented sensitivity of the James Webb Space Telescope to reveal it. When Webb looked at the earliest galaxies forming just 300 to 500 million years after the Big Bang, it found structures that had no business existing, yet according to the hierarchical model. Let me give you a specific example. In August 2023, astronomers announced the discovery of a galaxy designated JADES 140, which existed just 290 million years after the Big Bang. This galaxy is astonishingly bright and massive for its age. It contains roughly 500 million times the mass of our sun worth of stars. According to hierarchical models, building a galaxy this large this quickly requires an extraordinary level of efficiency in turning gas into stars, an efficiency we've never observed in the modern universe and that our models can't easily explain. Here's what will blow your mind. It gets worse. Webb found not just one or two of these impossible galaxies, but dozens of them. Galaxies that are too bright, too massive, too structured, too metal-rich for their age. It's as if the early universe was in a hurry, forming galaxies much faster than we thought possible. Dr. Ivo Laub, an astrophysicist at Swinburne University, was part of the team that discovered some of these early galaxies. He described his reaction as existential dread and excitement in equal measures. The data was forcing astronomers to confront the possibility that something fundamental was wrong with our understanding of galaxy formation. Several solutions have been proposed, and this is where it gets truly fascinating. One possibility is that the first stars were far more efficient at forming than we thought. In the dense, pristine conditions of the early universe, perhaps gas could collapse into stars more readily than our models predicted. If more mass converted into stars, and did so more quickly, that could explain these large early galaxies. Another possibility involves dark matter itself. What if the properties of dark matter particles allow them to clump together more efficiently in the early universe than our current models assume? This could create deeper gravitational wells, pulling in more gas, enabling more rapid star formation. This explanation would require adjusting our understanding of dark matter's fundamental nature. A third, more radical possibility has been suggested by some researchers. What if some of these early bright objects aren't actually galaxies at all, but supermassive black holes surrounded by incredibly luminous accretion disks? Black holes can generate enormous amounts of light as matter falls into them. If supermassive black holes formed earlier and grew faster than we thought possible, they could masquerade as galaxies in Webb's images. But this explanation creates its own problems, because it pushes the mystery one step deeper. How did supermassive black holes form so quickly? This leads us to one of the most profound questions in modern astrophysics. Let me introduce you to Dr. Priyamvada Natarajan, a theoretical astrophysicist at Yale University who specializes in black hole formation. In 2024, she proposed a controversial model for how the first supermassive black holes, some containing millions or even billions of solar masses, could have formed in the first few 100 million years after the Big Bang. Her model suggests that under specific conditions, clouds of gas in the early universe could collapse directly into black holes without forming stars first. These direct collapse black holes would begin their lives already massive, giving them a head start on growing into the supermassive monsters we observe. Think of it like this. Normally, a galaxy forms stars. Some stars die and leave behind stellar mass black holes weighing 10 to 100 times the mass of the Sun, and these gradually merge and grow by consuming gas. It's slow growth. But Natarajan's model is like starting with a massive seed that can grow much faster. It's the difference between growing a tree from a tiny seed versus planting a sapling that's already several feet tall. Recent observations have lent support to this idea. Webb has detected what appear to be little red dots, extremely compact, bright objects in the early universe that emit unusual amounts of X-rays and have spectral signatures suggesting they're massive black holes. Some of these black holes seem impossibly large for their age. There's even evidence of a black hole weighing 40 million solar masses, existing just 700 million years after the Big Bang. Growing a black hole this large through normal processes in that time frame requires it to be feeding at the absolute maximum rate, called the Eddington limit, continuously with no breaks, which seems highly unlikely. What we're witnessing is science in action. The James Webb Space Telescope hasn't broken the universe, but it has broken some of our theories about the universe, which is actually far more exciting. It means we're learning, we're discovering, we're being forced to think in new ways. Here's the revelation that connects everything. Galaxy formation isn't a simple, orderly process following predictable rules. It's a complex interaction between dark matter, normal matter, star formation, black hole growth, energetic feedback, mergers, and environmental effects, all playing out over cosmic timescales in ways we're only beginning to understand. The early universe was a more chaotic, more efficient, more surprising place than we imagined. And this brings us to a crucial question. Once these early galaxies formed, how did they grow? How did small proto-galaxies become the majestic spiral and elliptical galaxies we see today? The answer involves cosmic cannibalism on a scale that will fundamentally change how you think about the Milky Way. Your galaxy is a serial killer. Right now, at this very moment, the Milky Way is in the process of tearing apart and consuming at least 5 smaller dwarf galaxies. This isn't metaphorical. This is actually happening. And when I show you the evidence and explain the process, you'll never look at our home galaxy the same way again. Let's start with the most dramatic example, the Sagittarius Dwarf Elliptical Galaxy. In 1994, astronomers discovered something shocking. About 70,000 light-years from the center of our galaxy, on the opposite side from Earth, there's a small galaxy being ripped apart by the Milky Way's gravity. The Sagittarius dwarf contains roughly 1 billion stars, and it's currently plunging directly through the disk of the Milky Way. But here's what makes this discovery truly remarkable. This isn't the first time Sagittarius has passed through our galaxy. Astronomers can track its orbit backward in time and forward into the future. The Sagittarius dwarf has already made at least 3 complete orbits through the Milky Way, passing through our galactic disk, emerging on the other side, swinging around, and plunging through again. Each time it passes through, the Milky Way's tidal forces stretch it, pulling stars away from it in long streams that wrap around our galaxy. Think of it like this. Imagine swinging a water balloon on a rope in circles above your head. Now imagine that balloon is flying through a pool while you're swinging it. The water in the pool creates drag, slowing the balloon and pulling at it. That's similar to what's happening to the Sagittarius dwarf as it passes through the dense disk of the Milky Way. Except instead of water molecules, we're talking about the gravitational pull of hundreds of billions of stars, plus dark matter. Astronomers have mapped the debris trail left by Sagittarius, and it's spectacular. There are streams of stars wrapped completely around our galaxy, like ribbons around a gift. These stars were once part of Sagittarius, but they've been pulled away and now orbit the Milky Way independently. Some of these stripped stars pass right through our solar neighborhood. There's a reasonable chance that when you look at the night sky, some of the stars you're seeing were born in a completely different galaxy and are refugees from a cosmic collision. The Sagittarius dwarf will eventually be completely torn apart and absorbed. Its stars will become Milky Way stars. Its death is our growth. Galactic cannibalism in action. But Sagittarius isn't alone. The Milky Way is also consuming the Canis Major dwarf galaxy, which is even closer, just 25,000 light-years from us. Then there's the Fornax dwarf, the Sculptor dwarf, and several others, all being slowly digested by our galaxy's gravity. The process is slow by human standards, taking hundreds of millions or billions of years, but it's relentless and inevitable. Here's what will blow your mind. This process isn't rare or unusual. This is how galaxies grow. Galaxy mergers and acquisitions are one of the primary mechanisms by which galaxies increase their mass and change their structure over cosmic time. Our galaxy has been doing this throughout its entire existence. Dr. Vasily Belakurov, an astronomer at the University of Cambridge, has spent years studying the archaeology of our galaxy, looking for evidence of past mergers hidden in the motion and composition of stars. In 2018, his team made a stunning discovery using data from the Gaia spacecraft, which precisely measures the positions and velocities of over 1 billion stars in our galaxy. Belakurov found evidence of a massive ancient merger, what he calls the Gaia-Enceladus collision. About 10 billion years ago, when our galaxy was much younger, a dwarf galaxy containing tens of billions of stars collided with the Milky Way and was completely absorbed. This merger was so violent that it fundamentally altered the structure of our galaxy. It puffed up our galactic disk, scattered stars into the halo surrounding our galaxy, and possibly even triggered a burst of new star formation. Here's the revelation. A significant fraction of the stars in our galaxy, possibly 20%, or more of the stars in the Milky Way's halo, were born in other galaxies and later captured. Our galaxy is a mosaic, a collection of stars from many different origins all mixed together. When you look at stars in the night sky, you're seeing not just the Milky Way's native population, but also immigrants from dozens of smaller galaxies that were absorbed over billions of years. And it's not just small galaxies that merge. Large galaxies collide with other large galaxies, creating spectacular cosmic train wrecks. The most famous example currently underway is the collision between the Andromeda Galaxy and the Milky Way. Yes, you read that correctly. We're currently on a collision course with our nearest large galactic neighbor. Andromeda, also called M31, is about 2.5 million light-years away from us. That sounds far, but in cosmic terms, It's practically next door. And here's the kicker. It's moving toward us at about 110 kilometers per second. In approximately 4.5 billion years, give or take, Andromeda and the Milky Way will collide. Now, before you panic, I need to explain what a galaxy collision actually means. When galaxies collide, individual stars almost never collide with each other. Space is so vast, and stars are so small relative to the distances between them, that two galaxies can pass completely through each other with essentially zero star-on-star collisions. It's like throwing two swarms of gnats at each other. The swarms will intermingle, but individual gnats won't hit each other. What does collide is the gas. When the gas clouds from two galaxies collide, they slam into each other, compress, heat up, and trigger massive bursts of star formation. Galaxy collisions are stellar baby booms. The Hubble Space Telescope has captured beautiful images of colliding galaxies with brilliant regions of intense star formation at the collision sites. Regions so bright they outshine the rest of both galaxies combined. But the real drama comes from gravity. As two galaxies pass through each other, their gravitational interactions create tidal forces that stretch and distort both galaxies. Spiral arms are pulled out into long tails. Stars are flung into new orbits. The orderly disk structure gets scrambled. Computer simulations of galaxy collisions show that the galaxies can pass through each other, and their mutual gravity pulls them back together for a second collision, and sometimes a third. Each collision is slower than the last as the galaxies lose energy. Eventually, after multiple passes, the two galaxies merge completely into a single larger galaxy. The result is almost always an elliptical galaxy. Those beautiful spiral structures, they're fragile. A major collision destroys them. The disk gets puffed up into a more spherical shape. The orderly rotation is disrupted, replaced by stars moving in random directions. This is why elliptical galaxies are common in dense galaxy clusters where mergers are frequent, while spiral galaxies like our Milky Way are more common in less crowded regions of space where they've avoided major collisions. When the Milky Way and Andromeda merge, the combined galaxy, which some astronomers have already nicknamed Milkomeda, will be an elliptical galaxy. The beautiful spiral structure of both galaxies will be lost forever, transformed into a more amorphous blob of stars. Our solar system will likely survive the merger intact, but it will end up in a very different galactic environment, possibly ejected into the outer regions of the merged galaxy, or even into intergalactic space. Think about the timescales here. This collision is scheduled for 4.5 billion years from now. For context, 4.5 billion years ago, our solar system didn't exist. Earth didn't exist. The sun hadn't formed yet. That's how long the story we're part of really is. Here's the mind-bending truth. Galaxies are not static structures. They're dynamic, evolving, interacting entities engaged in a slow-motion cosmic dance. They grow by consuming smaller galaxies and occasionally merge with comparable-sized partners. Every large galaxy we see is a collection of many smaller galaxies that merge together. Galaxy evolution is a story of cannibalism, collisions, and constant transformation. But mergers are only part of the story. To truly understand how galaxies grow and change, we need to talk about what's happening inside galaxies between mergers, and this is where things get even stranger. Inside every galaxy, there's a hidden engine that controls its fate, and most people have no idea it exists. I'm talking about the supermassive black hole at the galactic center, and its relationship with star formation is one of the most surprising discoveries in modern astronomy. What I'm about to reveal will show you that black holes don't just destroy, they regulate, they control, and in a very real sense, they're the reason you exist. Let's start with a basic question. How do stars form? The answer seems simple. Stars form when clouds of gas and dust in space become dense enough that gravity overwhelms the internal pressure, causing the cloud to collapse. As the collapsing material concentrates, it heats up due to gravitational compression. And if enough mass collects and temperatures rise high enough, nuclear fusion ignites in the core. A star is born. In galaxies, this happens in giant molecular clouds, vast regions of cold, dense gas, mostly hydrogen molecules, sometimes containing enough mass to form thousands or millions of stars. These clouds are the cosmic nurseries, the birthplaces of stars. The Milky Way contains thousands of these molecular clouds, and collectively they contain billions of solar masses worth of gas available for star formation. Here's what's interesting. If you calculate how much gas is available and how efficiently it should collapse into stars, galaxies should be forming stars much faster than they actually are. Our galaxy currently forms about 1 to 2 solar masses worth of new stars per year. But based on the amount of available gas, it should be forming 10 times that many. Something is suppressing star formation, preventing galaxies from converting their gas into stars too quickly. For a long time, this was a mystery. Then astronomers realized something profound. The supermassive black holes at galaxy centers are regulating star formation across the entire galaxy. And the mechanism is both elegant and violent. Every large galaxy contains a supermassive black hole at its center. The Milky Way's central black hole, called Sagittarius A*, pronounced Sagittarius S*, weighs about 4 million times the mass of our Sun. Andromeda's central black hole is much larger, about 100 million solar masses. Some galaxies have black holes weighing billions of solar masses. These aren't stellar mass black holes formed from dying stars. These are monsters, and how they grew so large is still an area of active research. But here's what makes them crucial for galaxy evolution. When gas falls toward a supermassive black hole, it doesn't fall straight in. Conservation of angular momentum causes the infalling gas to form a swirling disk called an accretion disk. Friction in this disk heats the gas to extreme temperatures, millions of degrees. This superheated gas radiates enormous amounts of energy, primarily in X-rays and ultraviolet light. An actively feeding black hole, what astronomers call an active galactic nucleus, or AGN, can outshine all the stars in the galaxy combined. But the really important effect comes from the jets. Under conditions that physicists are still trying to fully understand, some accreting black holes launch powerful jets of particles and radiation from their poles. These jets punch through the galaxy, traveling at a significant fraction of the speed of light and extending hundreds of thousands or even millions of light years into intergalactic space. When these jets and the radiation from the accretion disk interact with the gas in the galaxy, they heat it up and blow it away. This is called a GN feedback. The black hole literally prevents gas from cooling down and collapsing to form stars. It's like a cosmic thermostat, regulating the temperature of the galaxy's gas supply and controlling the rate of star formation. Dr. Andrea Merloni, an astrophysicist at the Max Planck Institute for Extraterrestrial Physics, has studied a GN feedback extensively using X-ray telescopes. In a 2023 paper, his team showed that the energy output from supermassive black holes correlates strongly with the star formation history of galaxies. Galaxies with more active black holes in their past show evidence of truncated star formation, as if the black hole turned off the star factory. Think of it like this. Without a GN feedback, a galaxy would convert its gas into stars too quickly, using up its fuel supply rapidly. The galaxy would end up as a red and dead, elliptical galaxy filled with old stars and no gas for new star formation. But with a GN feedback, the black hole prevents this rapid burnout. It spreads out star formation over a longer period, allowing the galaxy to maintain star formation for billions of years. In a strange way, black holes extend the life of star formation in galaxies. But here's what will blow your mind. There's a tight relationship between the mass of a galaxy's central supermassive black hole and the mass of its bulge, a central spherical component of stars. Measure the bulge mass, and you can predict the black hole mass with remarkable accuracy. The black hole is always about 0.1% to 0.2% of the bulge mass. Always. In every galaxy we've measured. This correlation, called the M-sigma relation, after the mathematical symbols used, is one of the most surprising discoveries in modern astronomy. It suggests that black holes and galaxies co-evolve. They grow together, influencing each other's development over cosmic time. The black hole regulates the galaxy's growth, but the galaxy also feeds the black hole. It's a symbiotic relationship, a cosmic feedback loop. How does this work? The leading theory goes like this. In the early universe, protogalaxies form and begin accumulating gas and forming stars. The central black hole begins to grow by consuming gas. As more gas flows into the center, the black hole grows larger and its feedback becomes stronger. This feedback heats the surrounding gas, suppressing star formation in the central regions, but also pushing gas outward into the galaxy's disk, where it can cool and form stars. Meanwhile, mergers with other galaxies can funnel more gas toward the center, feeding both star formation and black hole growth. The system naturally self-regulates toward the observed correlation. If the black hole grows too large too quickly, its feedback becomes so strong that it shuts off its own gas supply. If the black hole is too small, more gas flows in and it grows. The equilibrium is the M-sigma relation. But there's another layer to this story that's even more mind-bending. Let me introduce you to Dr. Priya Natarajan again, because her work extends beyond just black hole formation. She's also studied how supermassive black holes influence the formation of structure in the universe at the largest scales. Her research suggests that the energy output from accreting supermassive black holes in the early universe may have contributed to reionizing the universe, a critical transition that occurred about 400 million years after the Big Bang, when the first stars and galaxies began producing enough ultraviolet radiation to ionize the neutral hydrogen that filled all of space. This reionization fundamentally changed the universe's transparency and affected how subsequent generations of galaxies could form. So not only do supermassive black holes regulate their own host galaxies, they may have influenced the development of the entire cosmic web of structure. Here's the revelation that ties this together. Galaxies are not just collections of stars. They're complex ecosystems with multiple interacting components. Dark matter providing the gravitational scaffolding, gas providing the raw material for star formation, stars producing energy and heavy elements, and supermassive black holes regulating the entire system through feedback. Understanding galaxy evolution means understanding how all these components interact over billions of years. And nowhere is this more apparent than in the phenomenon of galaxy quenching, the process by which star-forming galaxies stop forming stars and become red and dead. This transition is common in the universe, especially in dense environments like galaxy clusters. And the mechanisms behind it reveal just how interconnected galaxy evolution really is. There's a galactic graveyard in the universe, filled with dead galaxies that ran out of gas and ceased forming new stars billions of years ago. These red, elliptical galaxies contain trillions of old stars slowly fading away, with no bright young stars to replace them. And the processes that killed them are operating on galaxies everywhere, including our own Milky Way. Understanding how galaxies die is just as important as understanding how they're born. When astronomers look at galaxies in the modern universe, they notice something striking. There are two distinct populations. Blue, spiral galaxies actively forming stars. Their disks filled with bright, young, hot blue stars and glowing regions of ionized gas-marking stellar nurseries. And red, elliptical galaxies, smooth, featureless, dominated by old, cool, reddish stars with no ongoing star formation. There's a gap between these populations called the Green Valley, where galaxies in transition are relatively rare. Galaxies seem to move from blue and star-forming to red and dead relatively quickly, at least on cosmic timescales, typically within a billion years or so. This transition is called galaxy quenching, and understanding what causes it has been one of the major challenges in extragalactic astronomy. Because here's the thing, it's not just one process. It's several different processes, operating in different environments, on different timescales, and sometimes working together. Let me walk you through the main quenching mechanisms, and I promise, each one is stranger than the last. First, there's merger-driven quenching. When two gas-rich galaxies collide, the merger triggers an intense burst of star formation, what astronomers call a starburst. Gas clouds collide, compress, and fragment into massive clusters of new stars. A galaxy can become thousands of times more luminous than normal, forming stars at rates of hundreds or even thousands of solar masses per year. But this burst is self-limiting. The massive stars formed in the starburst live fast and die young, exploding as supernova within a few million years. These explosions generate powerful winds that blow gas out of the galaxy entirely. At the same time, the merger funnels gas toward the central supermassive black hole, causing it to grow rapidly and become an active galactic nucleus with strong feedback. Between the supernova-driven winds and the AGN feedback, the galaxy loses its gas supply. With no gas remaining, star formation ceases. The galaxy becomes quenched. This process can transform a blue, star-forming spiral galaxy into a red, dead elliptical galaxy in as little as a few 100 million years. It's a fast, violent path to quenching, and it explains why elliptical galaxies are often found in environments where mergers are common, like the centers of galaxy clusters. But there's another mechanism that operates specifically in those dense environments, and it's called ram pressure stripping. Imagine you're driving a convertible with the top down at high speed. The wind whips through your hair, pulling loose anything that's not tightly secured. That's essentially what happens to galaxies moving through galaxy clusters. Galaxy clusters aren't empty space. They're filled with hot, thin gas called the intracluster medium, heated to tens of millions of degrees by the gravitational energy of the cluster. This gas is tenuous, with a density much lower than the best laboratory vacuum on Earth. But there's a lot of it, and galaxies moving through it experience a pressure force, like a headwind. If a galaxy is moving fast enough, this ram pressure can strip the cold gas from the galaxy's disk, especially from its outer regions where the gas is more loosely bound. Astronomers have captured beautiful images of galaxies in clusters with long tails of stripped gas streaming behind them like cosmic contrails. Once the gas is removed, star formation shuts down. The galaxy becomes quenched. This process is particularly effective on small, low-mass galaxies, which have weaker gravity and can't hold on to their gas as tightly. In rich galaxy clusters, the majority of small galaxies have been quenched by ram pressure stripping, leaving behind red, gas-poor dwarf elliptical galaxies called cluster dwarfs. Then there's a more insidious process called strangulation or starvation. Galaxies don't form stars just from the gas they currently contain. They also continuously accrete gas from their surroundings, fresh fuel falling in from the intergalactic medium. This accretion is particularly important for maintaining star formation in the outskirts of galactic disks. But in galaxy clusters, or when a galaxy falls into a larger structure like a group of galaxies, this accretion can be cut off. The hot intracluster medium can prevent cool gas from falling into the galaxy. Without fresh gas inflow, the galaxy slowly consumes its existing gas supply through star formation and outflows. Over time, the galaxy stars, gradually fading as its star formation rate declines. This process is slower than ram pressure stripping or merger-driven quenching, taking 1 to 2 billion years, but it's very effective. What makes strangulation particularly interesting is that it affects different parts of a galaxy at different times. The outer disk, which depends most heavily on gas accretion, quenches first. Star formation gradually shuts down from the outside in. Astronomers can observe galaxies caught in this process, with quenched outer regions and still active inner regions slowly dying from the outside. Here's what will blow your mind. These quenching mechanisms don't operate in isolation. They work together, often in sequence. A galaxy might fall into a cluster, have its gas accretion shut off by strangulation, then later experience ram pressure stripping as it moves through the cluster core, and potentially undergo a merger that delivers the final blow. The combination is deadly. Dr. Bianca Poggianti, an astronomer at the INAFI Padova Observatory in Italy, has spent years studying galaxies and clusters using data from telescopes like Hubble and the Very Large Telescope. In 2017, she published a study of a galaxy cluster called Abell 2744, documenting multiple galaxies caught in various stages of ram pressure stripping. The images are dramatic, showing galaxies with their gas stripped away in real time, caught in the act of being quenched. One galaxy in particular, nicknamed the Jellyfish Galaxy because of its long tentacles of stripped gas, shows evidence of star formation happening in the stripped gas itself, not in the galaxy disk. The compression from ram pressure is triggering star formation in the tail. The galaxy is forming stars, even as it's being stripped of its ability to form stars in the future. It's simultaneously living and dying. This brings me to a crucial realization. Galaxy quenching isn't just about stopping star formation. It's about transforming the entire structure and nature of the galaxy. When a spiral galaxy is quenched, it doesn't just stop making stars. Over time, without new star formation, the bright blue stars fade away. The remaining old red stars become dominant. The gas disk, no longer replenished, dissipates. Without the gas disk's gravitational influence, orbits become more random, and the orderly rotation of the spiral structure breaks down. The galaxy evolves into an elliptical, environmental quenching. The collective term for processes like ram pressure stripping and strangulation is one of the main reasons why galaxy properties depend so strongly on environment. In the field, far from clusters, galaxies can continue forming stars for billions of years, maintaining their spiral structure and blue color. In clusters, galaxies are quenched, transforming into red ellipticals. The universe is painted in gradients, with galaxy properties changing systematically from dense to sparse environments. But here's the twist that most people don't realize. Our own Milky Way will eventually be quenched. Not from environmental effects. We're not in a cluster, but from the inside out. As our galaxy ages, the rate of gas accretion from the intergalactic medium is declining. Our Sun and solar system are actually living during one of the most active periods of star formation in the Milky Way's history. Over the next few billion years, star formation in our galaxy will gradually slow. Fewer and fewer new stars will be born. The galaxy will slowly redden as its blue stars die and are replaced. And then, in about 4.5 billion years, the collision with Andromeda will trigger a final starburst, consuming most of the remaining gas in both galaxies. After that burst fades, Andromeda will be a quenched elliptical galaxy, red and dead, slowly fading over trillions of years. Think about what this means. The night sky you see today, filled with thousands of visible stars and glowing nebulae marking regions of star birth, is not eternal. It's a temporary phase in our galaxy's evolution. Trillions of years from now, any civilizations living in Andromeda will see a very different night sky, one with no nebulae, no young bright stars, just the slow fade of ancient suns. Here's the revelation. Galaxies have life cycles, birth, growth, maturity, and death, just like living organisms. And just like organisms, the environment plays a crucial role in determining their fate. But unlike organisms, these cycles play out over billions of years, timescales so vast that they're almost incomprehensible. And that brings us to the biggest question of all. Where is all of this heading? What does the far future hold for galaxies? And what does that mean for the ultimate fate of the universe? The universe has a dark fate awaiting it, and when you understand what's coming, it will change how you think about everything we've discussed so far. Because all of this, the birth of galaxies, their growth, their interactions, their slow transformation, is all happening within a universe that itself is evolving toward an ending that's both beautiful and terrifying. Let me start with a discovery that shocked the astronomical community. In 1998, two teams of astronomers studying distant supernova made an observation that nobody expected. They were measuring how fast the universe's expansion is slowing down due to gravity, because that's what everyone assumed was happening. The Big Bang started the expansion, and gravity has been gradually slowing it ever since. The question was just how fast the slowdown was occurring, which would tell us whether the universe would eventually stop expanding and recollapse in a big crunch, or continue expanding forever, but at an ever-decreasing rate. But when Saul Perlmutter, Brian Schmidt, Adam Rees, and their teams analyzed their supernova data, they found something completely unexpected. The universe's expansion isn't slowing down, it's speeding up. Distant supernovae were fainter than expected, which meant they were farther away than expected, which meant the universe had expanded more than it should have if expansion was slowing down. The expansion is accelerating. This discovery was so shocking that both teams spent months checking and rechecking their data, looking for any possible error, because the implications were staggering. An accelerating expansion requires some form of energy that acts opposite to gravity, pushing things apart rather than pulling them together. This energy has been named dark energy, and it's the most abundant component of the universe. The current measurements show that ordinary matter, everything made of atoms, makes up only about 5% of the universe's total energy content. Dark matter makes up about 27%, and dark energy makes up about 68%. The universe is dominated by a mysterious form of energy that we don't understand at all, except that it's causing space itself to expand at an accelerating rate. Here's what this means for galaxies. The cosmic web of structure we discussed earlier, the filaments and clusters of galaxies, represents the largest structures that gravity has been able to pull together. But dark energy is working against gravity on large scales. As space expands and dark energy's influence grows, structures that are not already gravitationally bound will be pulled apart and separated by the expansion. In the far future, trillions of years from now, galaxy clusters will be isolated islands separated by vast, ever-growing voids. Galaxies not already bound together in clusters will drift beyond each other's cosmic horizons, regions of space expanding away from us faster than light can travel. Yes, that's possible. Space itself can expand faster than light. This doesn't violate relativity, because nothing is moving through space faster than light. Space itself is expanding. Eventually, billions of trillions of years in the future, any civilizations living in the universe will look out and see only the galaxies in their local group. Everything else will have been carried beyond the cosmic horizon by expansion. They will be able to see their own cluster of galaxies, but the rest of the universe will be invisible, unreachable, gone beyond the observable universe's boundary. But the story gets darker. Remember galaxy quenching? Eventually, all galaxies will be quenched. Star formation requires gas, and galaxies only have a finite supply of gas. Even with accretion from the intergalactic medium, which itself will slow and stop as the universe expands and the gas becomes more diffuse, eventually galaxies will run out of fuel. The last stars will form, and after that, no more. Dr. Fred Adams, a physicist at the University of Michigan, has mapped out the timeline of the far future in remarkable detail. According to his calculations, star formation in the universe will continue for about 100 trillion years, a timescale 10,000 times longer than the current age of the universe. But even 100 trillion years is finite. Eventually, the last star will form, burn through its fuel, and die. After that, the universe enters what Adams calls the degenerate era. The only objects remaining are stellar remnants, white dwarfs, neutron stars, and black holes, plus planets, asteroids, and other cold, dark objects. No new light is being created except for occasional flares when objects collide or fall into black holes. The universe becomes dark and cold. But even this is not the end. Over even longer timescales, measured in YY to YY years, protons themselves may decay. If protons are not stable, and many theories of physics predict they're not, just incredibly long-lived, then eventually even white dwarfs and other objects made of normal matter will slowly evaporate. The atoms making up these objects will literally disintegrate. After proton decay, the universe enters the black hole era. The only large structures remaining are black holes, ranging from stellar mass to supermassive. These black holes slowly evaporate through a process called Hawking radiation, where quantum effects at the event horizon cause black holes to emit particles and lose mass. The process is incredibly slow. A black hole with the mass of our Sun would take about 1,067 years to evaporate completely, but it's inevitable. Eventually, after roughly 10,100 years, even the supermassive black holes at the centers of galaxies, monsters weighing billions of solar masses, will have evaporated completely. The universe enters the dark era, containing only isolated electrons, positrons, photons, and neutrinos spread across a vast, cold, ever-expanding space. No structure, no complexity, no information processing, no life as we understand it. This is the heat death of the universe, the ultimate consequence of the second law of thermodynamics. Entropy, disorder, increases until maximum entropy is reached. Everything reaches the same temperature, just infinitesimally above absolute zero. No energy gradients remain to drive any processes. The universe achieves perfect, complete, eternal equilibrium. Now, I need to pause and acknowledge something. This cosmic eschatology is deeply speculative and depends on many assumptions that could be wrong. Proton decay is predicted, but has never been observed. Hawking radiation from black holes is theoretically very solid, but has never been directly detected. Dark energy's properties might change over time in ways we don't understand. There could be physics we don't know about that changes the story completely. But here's what makes this scenario compelling. It's based on our best current understanding of physics, and it follows logically from what we observe. The universe is expanding, accelerating, cooling. Stars are temporary. Structure is temporary. Even black holes are temporary. The logic leads inexorably to this cold, dark, empty end. And here's the truly mind-bending part. From the perspective of the far future, everything that has happened so far in cosmic history, including the entire age of stars and galaxies, is just a brief flash, a tiny fraction of the universe's total lifetime. We're living in the early universe, the first moments when conditions allow for complexity in life. Everything interesting, all the galaxy formation we've discussed, all the stars, all the planets, all the life, happens in this tiny window of time at the very beginning of cosmic history. Think about what this means for the story we've been telling. Galaxies aren't just born, grow, and change. They're born, grow, change, and then fade away, slowly dissolving as the universe expands and cools around them. The entire age of galaxies is an era, a phase in cosmic history, not the permanent state of the universe. But before you get too depressed about the heat death of the universe, billions of trillions of years in the future, let me tell you why this should actually fill you with wonder. Because there's another way to look at all of this that completely changes the meaning. You are made of stardust, and I don't mean that as a poetic metaphor. I mean it literally. Every atom in your body, except for hydrogen, was manufactured inside a star. And the evidence for this is written into the very elements that make you who you are. Understanding this connection between you and cosmic evolution is the key to grasping why galaxy evolution matters. Let's start with the atoms in your body. Your body contains about 7 octillion atoms. That's 7 followed by 27 zeros. The most common element in your body by number of atoms is hydrogen. About 60% of your atoms are hydrogen. But by mass, you're mostly oxygen, about 65%, with carbon making up 18%, hydrogen 10%, nitrogen 3%, calcium 1.5%, and phosphorus 1%, with traces of many other elements. Now here's the crucial point. Hydrogen is primordial. The hydrogen atoms in your body were created in the Big Bang itself, formed during the first few minutes of the universe's existence, when conditions were hot and dense, enough for nuclear fusion to occur. But every other element, oxygen, carbon, nitrogen, calcium, iron, everything else, was created in stars. Let me explain how this works, and it's going to reveal the deep connection between your existence and the life cycles of galaxies. After the Big Bang, the universe contained only hydrogen, helium, and trace amounts of lithium. That's it. No carbon, no oxygen, no iron, no silicon. All the elements heavier than lithium were created later through stellar nucleosynthesis, nuclear reactions occurring in the cores of stars. Stars like our Sun fuse hydrogen into helium in their cores, releasing energy. This is the power source of stars, and it's what makes them shine. But when a star exhausts the hydrogen in its core, if it's massive enough, it can begin fusing helium into heavier elements. Helium fuses into carbon and oxygen. In more massive stars, as successive fuels are exhausted, the core contracts and heats until the next fusion reaction can ignite. Carbon fuses into neon, magnesium, and sodium. Neon fuses into oxygen and magnesium. Oxygen fuses into silicon and sulfur. Silicon fuses into iron. The most massive stars end up with onion-like layers of different elements, each layer representing a different stage of fusion, with iron in the core, surrounded by layers of silicon, oxygen, neon, carbon, helium, and hydrogen. This process is building up the periodic table inside stars. But iron is the end of the line for fusion. Iron has the highest binding energy per nucleon of any element. Fusing iron into heavier elements doesn't release energy. It requires energy. So when a massive star's core is converted to iron, no more fusion can occur. The core can no longer support itself against gravity. Within seconds, the core collapses catastrophically, then rebounds in a core collapse supernova, one of the most violent events in the universe. This supernova explosion blasts the star's outer layers, including all those fusion products, into space at velocities of thousands of kilometers per second. But even more importantly, the extreme conditions during the supernova, with enormous temperatures, densities, and neutron fluxes, can create elements heavier than iron through rapid neutron capture, a process called the R process. Elements like gold, platinum, uranium, and thorium are created this way. In fact, recent observations have shown that neutron star collisions, not just supernova, may be the primary source of the heaviest elements. When two neutron stars spiral together and collide, the result is a kilonova, an explosion that creates and ejects significant quantities of heavy elements. The detection of gravitational waves from a neutron star merger in 2017, combined with observations of the light from the kilonova, confirmed that these events produce gold, platinum, and other precious metals. Here's what this means. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, were all created in stars that died before our solar system formed. When those stars exploded, they enriched the interstellar medium with heavy elements. That enriched gas eventually collected into new clouds that collapsed to form new stars and planets. Our Sun is a third-generation star, formed from gas that had been processed through previous generations of stars. You are literally made of recycled star guts. You are the ashes of long-dead stars, reconstituted into living, thinking matter. Carl Sagan said we're made of star stuff, but the reality is even more poetic. We're made of the hearts of stars that lived, died, and exploded billions of years before the Sun existed. But this process depends crucially on galaxy evolution. Here's why. The first generation of stars. Those population 3 stars formed in the first few 100 million years after the Big Bang contained no heavy elements. They were pure hydrogen and helium. When they died and exploded, they created and dispersed the first heavy elements into the universe. Those heavy elements were incorporated into the next generation of stars. Those stars created more heavy elements. Each generation increased the metallicity, the abundance of elements heavier than hydrogen and helium of the galaxy. This process is called chemical evolution, and it's a crucial part of galaxy evolution. Our solar system formed 4.6 billion years ago from a molecular cloud that had a metallicity roughly similar to the Sun's. About 1.4% of the Sun's mass is elements heavier than helium. This metallicity is high enough to form rocky planets. With lower metallicity, you might only get gas giants and ice giants, but not rocky terrestrial planets. And rocky planets are apparently necessary for life as we know it. Life requires complex chemistry involving carbon, oxygen, nitrogen, phosphorus, sulfur, and many other elements. These elements must be available in sufficient quantities, and they must be able to form complex compounds. Rocky planets provide stable surfaces where complex chemistry can occur over long periods. The chemical evolution of galaxies is directly linked to the possibility of life. Dr. Jennifer Johnson, an astronomer at Ohio State University, studies the chemical evolution of the Milky Way using spectroscopy to measure elemental abundances in stars. Her work has shown that the metallicity of stars in our galaxy increases over time, but also varies with location. Stars near the galactic center tend to have higher metallicity than stars in the outer disk, because the star formation rate has been higher near the center, producing more supernova and enriching the gas more quickly. The Sun's location, about 26,000 light-years from the galactic center, is in what some astronomers call the galactic habitable zone, a region where metallicity is high enough to form rocky planets, but supernova are infrequent enough that they don't sterilize planets with radiation too often. We exist not just at a particular time in galactic evolution, but also at a particular place. Here's the revelation that connects everything. You are not separate from cosmic evolution. You are part of it. The story of how galaxies form, grow, and change is your origin story. The elements in your body were created by specific processes: fusion in stellar cores and R-process nucleosynthesis in supernova and neutron star mergers that only occur as part of galaxy evolution. The conditions that allow for your existence, a metal-rich molecular cloud giving rise to a star with rocky planets in a relatively safe galactic neighborhood, are the result of billions of years of galactic evolution. You're not just living in a galaxy. You're a product of the galaxy's evolution, a temporary, localized concentration of complexity arising from billions of years of stellar processing. When you understand galaxy evolution, you're learning your own history, the deep history that predates not just human civilization or life on Earth, but Earth itself, the solar system, even the sun. And here's the truly mind-blowing part. This story is being written right now. The Milky Way is still evolving. Star formation is still occurring. Heavy elements are still being created and dispersed. Future generations of stars and planets will form from gas enriched by the stars living today. The sun will die in about 5 billion years, and when it does, it will return much of its mass to the interstellar medium. Some of the atoms currently in your body will eventually be incorporated into new stars, new planets, perhaps even new life. You are a temporary arrangement of star stuff, borrowed from the galaxy for a brief moment, cosmic scales, before being returned. But in that brief moment, you are aware. You can understand your origins. You can contemplate the vast timescales and enormous energies that made you possible. You can feel wonder at the improbability and beauty of your existence. And that brings me to the most important question of all. Why does any of this matter? In a universe heading toward heat death, in a cosmos where everything is temporary, where even galaxies will fade away, why should we care about understanding galaxy evolution? The answer is going to surprise you. Let me tell you something that most cosmologists don't emphasize enough. We are living in the most interesting time in the history of the universe. Not because of human civilization, though that's remarkable in its own right, but because of where we are in cosmic time. We exist during the stelliferous era, the age of stars, and this era, despite seeming eternal from our perspective, is actually a tiny fraction of the universe's total lifetime. Think about the cosmic timeline. The Big Bang happened 13.8 billion years ago. Star formation began within a few 100 million years. Star formation will continue for roughly 100 trillion years. That sounds like a long time, and it is, but compared to the 10,100 years or more until the final black holes evaporate, it's nothing. It's 0.00000000001% of the universe's lifetime. We're living in the first moments, the opening act, the brief period when the universe is interesting. And more specifically, we're living during the peak of star formation in cosmic history. Astronomers can measure the star formation rate of the universe as a function of time by observing galaxies at different distances, and therefore different look-back times. What they've found is that star formation peaked about 10 billion years ago, roughly 3 to 4 billion years after the Big Bang. Since then, the cosmic star formation rate has been declining, and it will continue to decline until star formation ceases entirely. We're living on the downslope in a universe that's slowly winding down. But we're still close enough to the peak that galaxies are active, stars are forming, the night sky is bright. We're in the sweet spot. Here's why this matters. The fact that we exist now, during this brief window, is not a coincidence. It couldn't be otherwise. Life as we know it requires stars, planets, heavy elements, stable environments, and time for evolution. These conditions only exist during the stelliferous era, and only after enough time has passed for chemical evolution to produce sufficient metallicity for rocky planets. Life couldn't have arisen in the first billion years of the universe because there weren't enough heavy elements yet. Life probably won't arise in the far future when star formation has ceased and no new planets are forming. There's a habitable epoch in cosmic history, and we're in it. This leads to a profound realization that was articulated by Brandon Carter in 1973 and is called the weak anthropic principle. The observed values of physical and cosmological quantities are not equally probable, but take on values restricted by the requirement that there exist sites where carbon-based life can evolve and observers can exist. In simpler terms, we observe the universe to have properties compatible with our existence, because if it didn't have those properties, we wouldn't be here to observe it. This principle has deep implications for how we think about galaxy evolution and our place in the cosmos. The fact that we find ourselves in a galaxy with sufficient metallicity, in an era with active star formation, in a relatively safe neighborhood, isn't surprising. These conditions are necessary for our existence. We're selection-biased observers. But here's where it gets philosophically interesting. Does our existence tell us anything about the universe beyond our local environment? This is where the strong anthropic principle comes in, and it's much more controversial. The strong version suggests that the universe must have properties that allow life to develop at some point in its history. This is a much bolder claim and ventures into territory that many scientists find uncomfortable because it seems to imply purpose or design. I'm not going to advocate for or against the strong anthropic principle here, but I will say this. The more we learn about galaxy evolution, stellar evolution, and planet formation, the more remarkable it seems that we exist at all. The number of things that had to go right, the precise values of physical constants required for atoms to be stable, stars to form, and galaxies to evolve in ways that create sufficient heavy elements, is staggering. Change the strength of gravity slightly, and stars either burn too quickly or never ignite. Change the nuclear forces slightly, and carbon might not form or might be too unstable. Change the amount of dark energy, and either galaxies never form because the universe expands too quickly, or the universe collapses in a big crunch before stars can evolve. The universe seems fine-tuned for the existence of complexity. Some physicists interpret this as evidence for a multiverse, the idea that there are many universes with different physical constants, and we naturally find ourselves in one compatible with our existence. Others see it as evidence for design, though most scientists are skeptical of this interpretation. Still others argue there's no fine-tuning at all, that we simply don't yet understand why the constants have the values they do, and that future physical theories will show they couldn't be otherwise. I don't know which interpretation is correct. Nobody does. But what I do know is this: understanding galaxy evolution gives us a framework for thinking about these deep questions. It shows us that our existence is contingent on a long chain of cosmic events, from quantum fluctuations in the first fraction of a second after the Big Bang, to the formation of the first stars, to billions of years of galactic chemical evolution, to the formation of our solar system. Dr. Martin Rees, the Astronomer Royal of the United Kingdom, has written extensively about cosmic fine-tuning and our place in the universe. In his book, Just Six Numbers, he argues that six-dimensionless physical constants determine the properties of our universe, and if any of these numbers were slightly different, the universe would be completely different, likely incapable of supporting life. His work emphasizes both how remarkable it is that we exist and how much we still don't understand about why the universe has the properties it does. Here's the perspective I want to leave you with. Studying galaxy evolution isn't just about learning facts about distant objects in space. It's about understanding the context of our existence, the narrative arc that led from the Big Bang to you reading this script. It's about recognizing that you are part of a cosmic story that's still being written, that the galaxy you live in is still evolving, that star formation is still occurring, that new planets are still forming. And it's about appreciating the improbability and fragility of your existence. You are a pattern in the cosmos, a temporary, localized violation of the universe's trend toward increasing entropy. You are the universe becoming aware of itself, matter organized in such a way that it can contemplate matter. In a universe that will eventually fade into cold, dark equilibrium, you are a spark of warmth and light and complexity. You exist during the most interesting era of cosmic history, in a galaxy that has evolved to have the right properties to support life, on a planet in the habitable zone of a stable star, at a time when that star has billions of years of life remaining. None of this is guaranteed. None of this is permanent. But right now, it's real. You are real. Your consciousness, your awareness of galaxy evolution, your ability to understand your cosmic origins, is one of the most remarkable phenomena in the universe. And that's why galaxy evolution matters. Because it's your story. Let me reveal something that will change how you see the night sky forever. Every photon of starlight entering your eye has traveled for years, decades, centuries, or even millennia to reach you. When you look at the night sky, you're not seeing the galaxy as it is now. You're seeing the galaxy as it was. You're looking back in time. And understanding this temporal dimension is crucial to understanding how astronomers study galaxy evolution. The speed of light is finite, about 300,000 kilometers per second. That's fast, but space is vast. Light from the sun takes 8 minutes to reach Earth. Light from the nearest star system, Alpha Centauri, takes 4.3 years. Light from the center of our galaxy takes 26,000 years. When you look at the Andromeda Galaxy, the photons entering your eyes left that galaxy 2.5 million years ago, before humans existed. This time delay is usually thought of as a limitation, but astronomers have turned it into one of the most powerful tools for studying cosmic evolution. Because when we look at distant objects, we see them as they were in the past. We can directly observe how galaxies change over time by looking at galaxies at different distances. Here's how it works. Astronomers identified galaxies at different redshifts. Redshift is the stretching of light wavelengths due to the expansion of the universe. More distant galaxies have higher redshifts because the universe has expanded more during the time their light has been traveling to us. By measuring a galaxy's redshift, we can calculate its distance and its look-back time, how long ago the light we're seeing was emitted. This means we can take snapshots of galaxy populations at different cosmic epochs. We can observe galaxies as they appeared 1 billion years ago, 5 billion years ago, 10 billion years ago. We can't watch a single galaxy evolve. That would require observing for billions of years. But we can observe many galaxies at different stages of evolution and piece together the story. This technique has revealed dramatic evolution in galaxy properties over cosmic time. In the nearby universe, we see a mix of spiral and elliptical galaxies, with many large, massive galaxies and a declining star formation rate. But when we look at galaxies at high redshift, we see a very different population. High redshift galaxies, observed as they appeared 10 to 12 billion years ago, tend to be smaller, more irregular, more gas-rich, and forming stars more rapidly than nearby galaxies. They look like the proto-galaxies and dwarf galaxies we discussed earlier, actively growing through mergers and accretion. The more distant we look, the earlier in cosmic history, the more chaotic and actively evolving galaxies appear. One of the most important discoveries from this approach is the mass assembly history of galaxies. By observing galaxies at different redshifts and measuring their masses, astronomers have reconstructed how galaxies grow over time. What they've found is that massive galaxies like the Milky Way have assembled most of their mass over the past 10 billion years through a combination of star formation and mergers. The most massive galaxies in the universe today were much smaller 10 billion years ago. But here's the surprising part. Massive galaxies seem to assemble their mass earlier than less massive galaxies. The most massive elliptical galaxies in the universe appear to have formed most of their stars 10 to 12 billion years ago and have been relatively quiescent since then. They underwent rapid, early assembly and then stopped. Smaller galaxies, by contrast, have been forming stars more gradually over longer timescales. This pattern is called downsizing, and it's somewhat counterintuitive. You might expect that larger galaxies, having more gravity, would take longer to assemble. But the data shows the opposite. The explanation seems to involve a GN feedback. The most massive galaxies have the most massive black holes, which produce the strongest feedback, quenching star formation earliest. Less massive galaxies have weaker feedback and can continue forming stars for longer. Dr. Mauro Javolisco, an astronomer at the University of Massachusetts, has been a pioneer in studying high redshift galaxies. Using the Hubble Space Telescope's deep field observations, images of small patches of sky exposed for weeks to detect the faintest, most distant galaxies, he and his colleagues have mapped the properties of galaxies across cosmic time. His work has shown that galaxies 10 billion years ago were more compact, more irregular, and more actively star-forming than today's galaxies, confirming the picture of galaxies growing and settling over time. But the really exciting developments are happening right now with the James Webb Space Telescope. Webb's infrared sensitivity allows it to observe even more distant galaxies. Galaxies as they appeared just a few 100 million years after the Big Bang. And as I mentioned earlier, these observations are revealing galaxies that are more mature, more massive, and more structured than we expected, forcing us to revise our understanding of early galaxy evolution. This is science in action. We make observations, develop theories, make predictions, and then test those predictions with new observations. When new data contradicts our predictions, we don't give up. We revise our theories, develop new models, and make new predictions. This iterative process is how we refine our understanding. Here's what will blow your mind. The galaxies we're observing with Webb, the ones forming just a few 100 million years after the Big Bang, their light has been traveling through space for over 13 billion years. The photons that left those galaxies when they were young are just now arriving at Earth. We're receiving messages from the early universe, time capsules containing information about cosmic conditions billions of years ago. And here's the even more mind-bending part. Those distant galaxies still exist today. They're not 13 billion light years away anymore. Due to the expansion of the universe, they're now roughly 45 billion light years away, far beyond our observable horizon. We can see where they were and what they looked like 13 billion years ago, but we can never see where they are now or what they look like today. The light from their current state will never reach us because space is expanding too fast. This leads to a profound realization. Our knowledge of the universe is inherently limited by the speed of light and the expansion of space. There are regions of the universe we can never observe, not because we lack powerful enough telescopes, but because the light from those regions will never reach us. The observable universe has a boundary, the cosmic horizon, and everything beyond it is forever unknowable to us. But within our observable universe, within the cosmic horizon, we can observe a vast sample of galaxies at different stages of evolution, allowing us to reconstruct the story of galaxy formation and evolution over cosmic time. And what that story reveals is that galaxies are not static. They're dynamic, evolving entities shaped by processes operating on vast timescales. Think about what this means for our understanding of reality. The universe we observe is a patchwork of light from different times, different distances, different cosmic epochs, all arriving at Earth simultaneously.